Hey, so we're going to be talking about quantum computation today. So is everyone ready to nerd it up a bit? I kind of chose this topic because I thought it'd be something I could talk about and it would drive everyone away. So turns out it didn't work out that way. Anyway, so as Chris mentioned, there was a talk earlier. Chris gave a talk earlier on computation, on computability. Basically, he talked about Turing, Alan Turing, and how he came up with a machine that would that he used as kind of like an analytic device to figure out like what could be computed and what could not. And so basically, what his main thesis was that everything that this machine could compute was everything that could be computed. There's nothing that you can compute that couldn't be computed by this machine. And so after that discussion, there was the talk. The questions turned to quantum computers and what can quantum computers do. And I was listening to the questions going back and forth, and I realized one, that there's a lot of interest in quantum computation, and two, it sounded like everyone that was talking about it didn't really have the right language to talk about like what makes quantum computers different. And so I wanted to kind of like take this talk and talk about that a little bit more. By the way, that's not Chris, that's Andrew, just so you know. Google hates Chris, apparently. All right, so I'm just going to start off trying to give an idea of what a quantum computation is all about, quantum computers are all about. And I'll start with the history. And so this is kind of like a history. Whenever you have like a big kind of area of research like this, there's always like a lot of people are involved. There are a lot of stories, but I can't really go into all of that. So the main thing that happened is in the 30s, Turing and Church, they came up with the concept of computability and basically realized that there are like some problems that can be solved or computed that can be solved with a machine, which are basically, and we think that those are all the problems that anyone can solve, people or machines can solve, and some problems can't. So after that, people started coming up with other machines that could also do that had the same property. Von Neumann was one of them. He came up with a machine that had registers and OR gates and stuff like that, and that's actually what's running my slides right now. Then also there was, he also came up with the idea of like a single cell automata as a Turing complete machine. So there was basically ideas, you have a bunch of finite states in a grid and finite state machines, and these state machines can only talk to their neighbors. And it turns out you can set that up right. You can set up computations or problems in a finite automata and run it, and it's Turing complete. Everything works. And so what happened is over the next 50 years or so, like people kept coming up with more and more Turing complete machines, like different ways to think about computation. And it became easier and easier because all you have to do to prove something is like it's Turing complete is show that it can emulate something else that's Turing complete. And as you have more of those things, it becomes easier and easier to do. So at any rate, you get up to the 80s. Fredkin and Toffoli, and they had this idea where you take a pool table, a billiards table, but it's almost infinitely big, and there's no friction, and there's no, and all the collisions are elastic, perfectly elastic. And so what happens is, and you can set it up in such a way where you hit the cue ball, and everything's set up in diagonals, and the balls just go off in different directions. And if you set it up right, it is also a Turing complete computer. You can do computations with the billiard table. So I chose this image for it because one, it's kind of cool and it's a billiard table, and two, because this is kind of the point where computability jumped the shark. It's like after that, everything was Turing complete. So computability is not really that interesting a concept in that sense. It doesn't give you a lot of power to distinguish between some things and what things are and what they aren't. But this guy basically took that idea. Does anyone know who this guy is? Does anyone know who this guy is? Feynman? No? Yeah, okay, that's Richard Feynman. So he's a nut. So Richard Feynman like kind of took a big Sharpie and wrote his name all over 20th century physics, especially quantum physics. He's definitely one of the top 5 physicists of the 20th century. And he was teaching at Caltech, and he heard about this billiard ball idea, and he was also thinking about like what's the smallest computer? Basically, at the time in the 80s, things were miniaturizing, and he was like, how far can that go? And he used this to reason that you could actually take quantum objects, basically atoms, things that are really small, and do kind of the same billiard ball trick and make a computer out of that, and that's how small things can get. But once you get down to that level where things are that small, you can't use classical mechanics anymore. You can't do the billiard ball trick. You have to use quantum mechanics. And so that's what he worked out, is how to use the quantum gates and how to use quantum tricks to actually make a computer like this. Now, he didn't really, I actually read his lectures from around that time, and he doesn't seem to really think of it as being able to do anything special. He's just like, this is a computer, it can compute everything, and it's really, really, really small. So that really was not a concept until the 90s that people started thinking about like computers, like quantum computers, actually being able to do things that classical computers just can't. So anyway, I don't have time. Okay, so it'd be kind of crazy to try to teach you quantum theory in about 30 or 45 minutes, right? So, because then I wouldn't have time to give the rest of the talk. So I'm going to try to teach you everything you need to know in 5 minutes. All right, so quantum theory, very basically, the most interesting, or one of the most interesting phenomena that happens when things are very, very small is that when you measure things, you can't measure them the way you can measure things in the classical world. What ends up happening is your measurement ends up interacting with it, and you stop getting like this kind of like real number, kind of like where things can come in all different kinds of positions and things like that. And so if you want to say measure the spin of an electron, you measure it, and you don't get that it has like a couple angles or something like that. What you get is that it's either up or down. That's all you can say, it's up or down. And so that is actually really good for a quantum computer because we have bits, right? Like our computers are made out of bits. They're like little logic gates, and we put a whole bunch of them together, and that gives us memory, that gives us registers and things like that. And so in the quantum world, when you do a quantum computer, you have something called a qubit. For a quantum bit. And there's lots of things that can be qubits. The only real requirement is that it has some kind of physical property that is either kind of up, down. It's like two-phase. So if you have photons, it's the polarization. So light can be polarized. It's kind of like sideways or up. Electrons have spin, which I just talked about. Atomic nuclei, they also have spins. These are all candidates for quantum computers. Quantum dots is when you have a very, very small cavity, like in silicon, you like make something really, really small, and it kind of has well, basically it starts to exhibit quantum phenomena there. I don't really know that much about that, but I do know this is probably a quantum dot computer. And what you don't see here is this is not actually running. If it were running, it would probably be bathed in liquid hydrogen and also in a big vacuum chamber because things have to be kept very, very stable to make this stuff work. All right. So this is probably the hardest slide in this talk. So I'm going to talk about superposition and entanglement now. So imagine these are qubits, right? And so you have you start off in a pure state. You always start off in a pure state and end up in a pure state when you measure it. And what that means is all the qubits actually have a value. They're on, off, they're spin up, they're spin down. And so like I'm representing this is spin up, that's spin down, that's spin up, for instance. Now what happens when you take a pure state like that and you apply some kind of quantum gate? Now quantum gate basically means a lot of different things in different contexts. But the idea is basically you're running these qubits and putting them into entangled states and like kind of mutating those entangled states. And what an entangled state is basically instead of being one or the other, where all these bits are one or the other, they end up being all the things. So basically every possible combination is kind of encapsulated in the entangled state. And they all have these coefficients next to them. And those coefficients are kind of like probabilities. And actually here's where it gets really cool. So what I want you to do is think with me for a little bit and just imagine probability theory. How many people here have taken probability theory, like some kind of probability class, know a little bit about it? All right. So probability theory just means that you're talking about things like betting odds, like blackjack, or like how likely are you to win the lottery. And so what happens is you basically, it comes out to be a lot of fancy ways of taking the number of things you want and dividing it by the number of possible things that could happen. But there's like a lot of mathematics reeled around it. And so, basically you always start with the probability of one thing happening. And now a probability is a number between 1 and 0, and it's a real number. So what I want you to do is think with me for a minute about what would happen if you didn't make that a real number from 1 to 0. What if you actually made it a complex number? -1 to 1 and also possibly imaginary. Now, don't actually think about that, because if you try to think of what an imaginary probability is and what the implications of that, your head will explode and it'll be a big mess. We'll have to clean it up and I won't have time to finish the talk. So, but if you just think about like what would happen if you just replaced all the probabilities in probability theory with complex numbers, the first thing you notice is that everything works. It's like the math still plays out. You would start to notice there are some interesting things, like you'd have probability distributions that aren't smooth. They actually kind of have lines in them, or like when you add things together. That's a consequence of things being positive and negative and things actually canceling out. The other thing you would notice if you were a physicist is that you would have basically reproduced the theory that it took decades of early 20th century physicists to come up with for quantum physics. Basically, quantum physics is really nothing but taking probability theory and using complex numbers for all the probabilities. And almost everything that's interesting about quantum mechanics comes out of the fact that the probabilities are complex. Definitely these entangled states, they're entangled because they're not entirely real. It's like they have an imaginary component, and so you have to take that into account. Superposition, the interference, all those things are really just come out of that naturally. And so it's a really kind of amazing thing. It's like quantum mechanics is weird, and it's like actually Niels Bohr said that if you are not profoundly shocked by quantum mechanics, then you just don't understand it well enough. But the thing is, even though quantum mechanics is really weird and it doesn't like correspond to our idea of the natural world, the math is actually relatively simple. So that's superposition. Oh, and I actually want to talk about like this. So this is kind of the idea of quantum computers can, some of you might have heard this, that quantum computers are fast because they have all the answers. They can go through, have all the answers in front of them and pull them out. That's not exactly true. So the thing is, like, the number pi, the digits in the number pi contain all the works of Shakespeare. That's like somewhere in there, they're in there because like there's enough permutations in it. If you go on infinitely, the trick is to get it out. And that's the thing with quantum mechanics is like it is somewhat true that all the answers are in the superposition for quantum mechanics. It's not actually true that it's just like the quantum computer can just look at the right answer and then have it come out. So, so I'm going to talk a little bit about what quantum computers can do. Well, the main thing, the reason we're actually interested in quantum computers is because they're, okay, first of all, quantum computers, the good news is quantum computers can do everything a Turing machine can do. They're Turing complete. You can show that, actually that's what Feynman showed in his paper, which is that you can, using quantum gates, you can do everything that you can do with classical gates. And actually do every computation on a quantum computer that you can do on a classical computer. So that's the good news. The bad news is it's just a Turing machine. The thing you can actually emulate a quantum computer on a classical computer. It's not very fast. That's the thing, is it takes a long time, but you can't compute anything you can't. So the computability for a quantum machine is the same as for a classical machine. So what we're really interested in is efficiency. We're trying to figure out like why, the thing is quantum computers, we have this idea that they're fast. And the idea is that they have because they can put everything in superposition, they can have everything at once, that they can do things faster. And so how fast are they? Well, in 2012, some researchers set a world record for the biggest number factored into primes. And now everyone knows that, well, people that know quantum computing know that factoring numbers into primes is actually something that quantum computers are known to be good at. And so they set the world record, 2012. It was that. So anyone still using 16-bit encryption keys, better watch out. So that is not a very big number. Actually, when I read this, I didn't give the answer, like what the factorization is. So I wrote a little JavaScript in the console to figure what it was, and basically it ran in essentially 0 time. So it's like you can't benchmark quantum computers right now. It's like you can't, they don't work with, they don't do enough things to make that happen. And so there's the concept that quantum computers are fast and they can do impressive things, but it's hard to say exactly what that means. And so I want to get into what we're actually talking about when we say that they're more efficient. And in order to do that, I'm going to talk about computational complexity theory. And so this is kind of the bait and switch part. I know you guys all came out here to hear about quantum computers. I really wanted to talk about computational complexity, and so you've already eaten your pizza. It's going to be awkward if you walk out the door now, so I kind of got you. So computational complexity is basically, it's a branch of computer science where, and this is like theoretical computer science, which is more like math, where you're trying to take problems and figure out what problems can be solved efficiently and what can't under certain conditions. And so when we talk about efficiency, you have to understand a little bit about, it's kind of a weird concept because, like, you know, you could have a problem and, you know, I could do it on my iPhone and it could take a long time, but I could run a supercomputer and it would happen really fast. And it's the same problem, so how can you say a problem is efficient or not? What we were actually talking about when we talk about computational complexity or algorithmic complexity is how does the time it takes to solve a problem increase as you increase the input size? So as you try to solve more of the problem, how is it, you know, how much harder does it get? And so there are some problems that are logarithmic, and so that's that blue line right there. And so what happens is they're actually getting a little bit easier to solve the longer it gets. It's not as hard to solve it as, you know, basically it takes less time the more input you put in relative to the amount of input you have. And then there's also linear, which is n. So basically you start with n inputs, so basically like n bits, say. And it'll take n steps to come out. It might be 5n or something like that. We don't really care about constants, right? But essentially it's going to be a straight line like that. And then also, you know, you can have like a quadratic curve like that. You could have like a n to the 100. Hopefully not. That's actually not efficient, but we're still going to call it somewhat efficient. And so all these things we call polynomial time. So basically, if there's a polynomial that will run that will always be greater than, there's a polynomial formula that will always be greater than the actual expression, which, the formula you use to say how long it takes to do an algorithm, we'll say that it's in polynomial time. And then, so not everything is in polynomial time. And so this is exponential. So here we have 2n. So like if you have n bits, say, it's going to take 2 to the n to solve it. So what that's saying. And you can see there's not a whole lot of difference between this and that. It's like here the n's on the bottom, the 2's on the top. Here the 2's on the bottom, the n's on the top. But exponential is different. It's actually, this is the mathematics of explosions. This is like things that go up really, really, really fast. And so there's basically a lot of technical reasons why we consider exponential to be, or different from polynomial, why we think polynomial time is kind of what it means to be efficient. But that kind of gets into some technical things. Basically, complexity theory, as far as complexity is concerned, we just go ahead and draw a line in the sand. And we're going to say that everything that falls in this polynomial camp is efficient. Everything that doesn't is everything that's above polynomial we call inefficient. And the main justification for that, it kind of corresponds to what actually happens in real life. It's like if we don't know an algorithm that runs in polynomial time, it probably runs really, really slowly, or it's not actually feasible to run it for large inputs. And if it's polynomial, usually it is. Not always, but often. Most of the time it is. And so, so this actually defines a computational class, and we're going to be talking about a lot of computational class. And so this is actually the computational class of P for polynomial, and this is the computational class of EXP for exponential. So almost everything that's interesting is an exponential. So now I'm going to talk a little bit about MP. So MP does not stand for not polynomial. It actually stands for non-deterministic polynomial for technical reasons. But this is another complexity class. And so this is the complexity class of all problems that can be checked efficiently. So basically, there's an algorithm that checks that you got the answer right. And so the example I'm going to give is not super accurate, but it's basically, hopefully it gives some insight. So say I give you a problem, and I give you a maze, and I want you to give me an algorithm that solves it. And it's actually, you can solve mazes fast, but if let's say you couldn't. So every algorithm that solves a maze, say it takes a really long time to do. So I give you this maze, and then you run your program, and it takes a day or a week or whatever to come back. But eventually, it does come back, and you give me a solution to the maze. When I get it, all I have to do is I have to check that you started in the right place, you ended in the right place, and that you never crossed a wall as you went through it. And I've checked that you have a solution, that it's actually a valid solution. And so my algorithm is actually really fast, but even if you don't have a fast algorithm. Now, if I gave you a maze that had a lot of options, and I didn't tell you to give me the right answer, or give me a answer, I told you to give me the fastest answer. Well, you would take a week or a month or a year or whatever to give me the answer back, and then I would check it, but in order to check it, I basically have to go through and check all the possible solutions to figure out whether or not there is one. So that would not be in NP. You can't check it fast enough, and so that's like an example of something that would be outside of it. So this is P equals NP. So basically things that we can solve in polynomial time versus things that are in non-deterministic polynomial. So basically this is asking whether there's anything that can be checked efficiently but not solved efficiently. And it's an open problem. It's actually probably the biggest open problem of our time. In fact, if you solved it, you would get millions of dollars or $1 million, because there's a Clay Millennial Prize for it. There's 10 Clay Millennial Prizes, one of which has been solved, one of which includes the Riemann hypothesis, and the rest of them I don't really recognize. But P equals NP is in there. Some people say this is like the most important problem that's out there right now. Some people even say this is like the most important problem for all of life. But those are usually computational complexity theorists. So one of the things about P equals NP is that we don't actually believe that it's true. We believe that P does not equal NP, that there are problems that are in NP but aren't in P. And that's a weird thing to say because this is math, and normally you prove things, you don't just believe things. And so I want to talk a little bit about why we do it. I think the main reason is it just kind of defies our intuition. I don't know if any of you are familiar with The Hitchhiker's Guide to the Galaxy, but there's this idea in it called the infinite improbability drive. And the idea is that you can make anything improbable happen, no matter how improbable it is, just by doing the calculation of how improbable it is and feeding that number into it. And if P did equal NP, that's kind of what we'd have. Basically, if there's any way that you could check a problem, you'd be able to solve it. That's what P equals NP is saying. What that means is all our proofs that we think as math is hard. We think that proving some things is really hard, but every proof can be checked fairly easily. And so if this is the case, math just shouldn't be hard. And Scott Aronson actually says that if P equals NP, then everyone that can appreciate a concert would be a Mozart. Everyone that can follow a step-by-step algorithm would be a Gauss. So that's part of the reason why we don't think that P equals NP. Also, at P equals NP, this is happening because we think things are hard. People think there are some things out there that are hard to solve, and some ideas that are hard to solve, even if they're easy to check. And if we continue to think that and it's not actually true, then it must be just some deficiency in our brain. We must not be able to understand things like everything that could be understood, and the machines are eventually they're going to figure that out, and this is going to happen. So, so I don't believe P equals NP, and most people don't believe it, but it's probably, people say it's going to be 30 to 100 years before anyone can solve it. It's a really, really hard problem. So So that's P equals NP. So now we have EXP, which encompasses almost everything that we're interested in. We have P, which is everything that we can solve efficiently. We have NP, which is everything that we can check efficiently. And now I'm going to talk about BPP, which is another class. So BPP is called bounded probabilistic polynomial time. And this is all the problems that can be solved so long as you give it like a random number source, and as long as you don't care that it gets the answer right all the time. In fact, it only has to get the answer right 2/3 of the time. And now that sounds dumb. Like, why would you want a computer that's only right 2/3 of the time? But what ends up happening is if it's right 2/3 of the time, you can run it twice. And then it's right more of the time. You can just take the majority answer. You can run it 3 times. You can run it 9 times. Eventually, you're going to get to the point where it's so improbable that it's not going to get the right answer. It's actually more likely that an asteroid would come and just like destroy my computer right now than it would get the answer wrong. So, and the thing is, like, just running it like 100 times or 200 times doesn't really change the efficiency of it all. So that all kind of works. And there was up until the 2000s, there was the main problem for BBP was finding primes, or finding the primality test, testing whether a really large number is prime. And Miller and Rabin, they came up with an algorithm, a randomized algorithm in BPP that where you take a number and you'd run this test on it. You basically mod it and use like Fermat's little theorem and things like that, and you come out with like an answer that say like if it's always 0, then, and this happened with a bunch of numbers, then it was almost certainly prime, or maybe it's the other way around. But so for a long time, this is like the biggest example because everyone thought that primality testing was hard, and if you do it randomized, they actually came up with an answer that was could be run fast. And then in 2006, some Indian researchers came along. I don't remember their names, but I know it ends with AKS. They came out and they found a probabilist, like a deterministic polynomial time algorithm for testing whether a big number is prime. And so what happened is once they did that problem, primality testing, suddenly became NP. And suddenly BPP is like not so interesting anymore. The irony is actually that algorithm, the AKS algorithm, is really, really complicated and no one actually uses it to test primes, and people still use Miller-Rabin all the time. It actually works really well. But the thing is, because of that, people are starting to suspect that BPP may actually be P. Like be the same thing as P. There's like no problems in P that aren't in BPP. All right, so this is actually why I brought all this stuff up. This is bounded quantum polynomial time is another computational complexity class, and this is all the problems that can be solved on a quantum computer. And so the big question right now is the class of problems that can be solved on a quantum computer different from the class of problems that can be solved on a classical computer? And the answer is probably yes. And this is the reason why. So Shor's algorithm is an algorithm to determine, well, basically it's an algorithm to factor numbers. So you have a large number and you want to factor it into primes because some people like to do that. You can use Shor's algorithm to do it. And the thing is, Shor's algorithm runs on a quantum computer efficiently, and it's pretty much been shown not to run on a classical computer efficiently. Just really, like at a high level, the way Shor's algorithm works is you have a big number, and this number is like, if it has factors, it's going to, basically you imagine those factors being able to take those factors and kind of separate the number up into a bunch of different blocks. And then, so what happens is you create a function that kind of looks like the way it's getting factored into all those different sections. And then you run what's called the quantum Fourier transform on it, which is a way to basically analyze the frequencies in a formula, in a function. And what it comes out with is whether there's a period to it, and whether this formula has a period. And if it has like a strong period, that indicates that it's a factor. And then you get the answer, which is that factor. It's definitely a lot more complicated than that. But Shor's algorithm suggests that BQP is not the same as BPP. And the reason why it doesn't actually just say that is because we don't know that factoring is actually hard. It may be that we could come up with a different polynomial algorithm for factoring. So there's actually several other algorithms that we know of. I copied these from Wikipedia. I have no idea what they do, and I don't think almost anyone knows what they do because they're math problems. They're not actually that useful. Grover's algorithm on the bottom here is kind of the bastard stepchild of complexity theory because it's actually a really useful problem. It's like an algorithm. It basically allows you to do a search on something that doesn't have an index and come up with a much faster answer on a quantum computer than you can come up with on a classical computer. So when you do that, so it's kind of like if you have a haystack, and that haystack has 1 million straws in it, in one needle. Using Grover's algorithm, you don't have to check 1,000 of those straws to figure out where the needle is, because it gives you a quadratic improvement. And that quadratic improvement is entirely due to the fact that the probabilities in quantum mechanics are complex. And so it's just the way the math works out. So it's really cool, but quadratic means you're not actually changing from an exponential to a polynomial time algorithm, so you don't actually, it's still in the same class, which is why complexity theorists don't really talk about it. All right, so just recap this a little bit. We have BPP, which is all randomized algorithms. We have BQP. BQP, well, first of all, BPP is probably just P. It's probably just polynomial time algorithms. BQP is all the algorithms, all the quantum time algorithms, and we think that it's different. Because of Shor's algorithm and some of these other algorithms, I think there's things that you can solve on quantum computers that you can't solve efficiently on classical computers. The BQP versus MP is actually a really interesting problem. A lot of people think because you can do factoring efficiently on quantum computers that quantum computers can do all MP problems. But it turns out that factoring is probably one of the easiest problems that are in MP but not NP. There's definitely a lot of harder problems. Factoring is not, so people think that it's really not that hard. It's also possible that BQP can do things that aren't even in NP. So that's because when you do NP, what you're actually saying is this is a problem that I can check on a classical computer. So if you have a quantum computer, you could actually be able to check the problems in quantum time. So there's some other reasons. Actually, it gets very technical why people think that they're disjoint, but that's kind of where it's heading out or landing. And so this is complexity theory. This is actually a very small set of it. There's actually a lot more classes, but you see these are all problems up here. These are all our exponential problems. These are things that we actually care about. There's a bunch of things. That's polynomial hierarchy. This is the poorly named PP. PP's over everything. So this is so there's NP down here. So P is definitely an NP. There's BQP, quantum programming in here. There's BPP down here. So quantum computers definitely can do everything that a classical probabilistic computer can do. Interestingly, we don't know that it can do everything. Well, no, sorry. Because of that, it is actually everything that's in polynomial time is actually in quantum computing. So as far as these two are concerned, they may be the same. That might get collapsed. As far as P is equals NP, we kind of hope that they're not the same. BQP may be under NP, it may be over NP. It's probably not over NP. It's probably not in NP either. Same thing with BPP. No, I'm sorry. BPP is actually probably in NP, but we haven't proven it yet. So, so anyway, this is like this is a complexity zoo, and it's. I mean, you can imagine if you took this like equals and is inside and outside. And replaced it with like sleeps with and in a coma and fell in love with. This is just like a big nerdy soap opera, and I think it's really exciting and delightful. But anyway, so encryption. This is what people kind of get excited about when we talk about quantum computing, and for good reason. So really quickly, most of the encryption that we use today is something called public key encryption. And the idea is it's usually RSA encryption. And the idea is that you take two fairly large prime numbers and you multiply them together and to get And well, you take one of those prime numbers is called your private key, and the two numbers multiplied together is called your public key. And so you send it out, and this is just kind of, probably I'm getting a lot of things wrong about this, but it's kind of the idea. So anyway, so you're the recipient of the message. So you have the private key and you have the public key, and you send your public key to the sender of the message. The sender of the message then takes the public key and runs some math on it. It's like they cube it, subtract 1 or something like that, and they and they come up with the encrypted text, and they send it back to the message sender, or to the recipient. And so the recipient, well, for one thing, because the number has been encoded with that large prime, or like the large composite number, it can't be, anyone looking at it can't figure out what's going on. It's like basically that step of cubing the message, or basically the math that the sender does, is really hard to reverse. And we still think that that's really hard to reverse, even with a quantum computer. So what happens, though, is they send it back to the message sender, and the message sender takes their prime number. And since they have the prime number, they're actually able to, the private key, they're able to figure out what the message actually said. And that's kind of what's going on with RSA, and that's probably mostly wrong, but it's the idea. And so the big problem with that is not that, like with a quantum computer, people will be able to take the encrypted text and somehow break it. The problem with it is that the message sender or message recipient has to send their public key unencrypted. And so that public key is just a big number that is the product of two prime numbers. And if you have a quantum computer, you can use Shor's algorithm to factor that number into the prime numbers, which is the private key. So all you have to do is you have to factor that number and then take that private key and do the exact same thing the message recipient would have done in the first place. And you've unencrypted the message. And so because of that, RSA is definitely toast. Like, the quantum computers become a real thing, and they might already be a real thing. RSA just doesn't work anymore. This is also true of elliptic curve cryptography. This is kind of like the next cryptography that's supposed to be a lot more secure. It turns out that you can actually factor, or you can use Shor's algorithm on that. It's a modification of Shor's algorithm on elliptic curves, and it's actually easier to do. So basically, there's not really any point in looking into these types of cryptography anymore, assuming anyone can actually make a computer that can do more than 16 bits. This doesn't mean this is the end of cryptography. There's actually different types of cryptography based on harder math, things that we think are harder that we don't think that quantum computers can do. This is really a fact. I mean, so the idea of RSA, the reason we use prime numbers and factoring in RSA is because it's kind of the easiest thing that we can do that we still think is hard to compute. So, and it is hard to compute with a quantum computer, with a classical computer. But unfortunately, quantum computers raise the bar just a little bit, and so it doesn't make any sense anymore. But there's no reason why we can't come up with other types of math that just raise the bar even higher, and probably quantum computers will not be able to solve that. So it's not the end of cryptography. It's just we got to switch off from RSA and elliptic curve, and probably soon. So you might have heard me mention Scott Aronson a few times. This is Quantum Computing Since Democracy. Everything I've told you today is in this book. This is a great, great book. Scott Aronson is one of those kind of rare people that's top researcher in this field, like really one of the best computer scientists out there, and also a great, great popular science writer. He's had a blog that's shuttle optimized that I've been reading for a long time. Everything he writes in this book is funny, which is weird because it's all math. But anyway, this part of the reason of this talk is just to get people to read this book. So I highly, highly encourage it. This is also good. So this is Feynman's lectures that he gave back in the 80s on computation to Caltech. And there's a chapter in it on quantum computation where he talks about what he did and like what a quantum computer would look like. But this is still back in the 80s. So it's a little disappointing. He doesn't actually talk about what quantum computers can do. He just talks about how you go about building one. But I still highly recommend the book because it's like, if you don't want to go out and get a computer science degree, or if you just kind of want to remember what was going on in computer science and you want to be entertained while you do it, Feynman's really good for that. He has a great way of explaining things. And that's it. So thanks, everyone.